In this lecture, we study association between quantitative variables or numerical variables. In the previous couple of lectures, we looked at association between categorical variables. Now we extend, we looked at measures like chi-square and Cramer's V for categorical variables, and we will try to find out what are the equivalent measures if we look at quantitative or numerical variables. Now, let us look at some data and let us say that we are trying to look at the association between salary and saving. So, we have two variables, one is the salary of the person and the other is the saving of the person. So, one of the variables acts as the x variable or the x axis variable, and the other variable acts as the y variable or the y axis variable. So, generally the explanatory variable is the x axis variable and the response variable is the y axis variable. So, in this example we can assume that the salary is the reason for saving, because people get income and salary from which they save, therefore, the saving becomes the y axis variable and the salary becomes the x axis variable. So, let us assume that we have some 100 pieces of data for salary and saving for a pair of x y, where x is the salary and y is the saving. And let us assume we have plotted this, and this is what we get if we plot these 100 pieces of data, each data having an x and a y value. Now, the same picture is shown on the left hand side, and let us look at this. Now, let us do something else, and then we started with 100 sets of data, each data having an x and each data having a y. Now, suppose we quickly randomize the x and y, in the sense we just quickly make a random sort of x and then a random sort of y, which means now with the new data the x and y are not exactly as they were paired in this data, and we still get 100 pairs with different x and different y, let us say kind of randomly chosen, and then we plot that using this and get this kind of a plot. So, this is the data and this is the random. Now, the first impression is that the data looks very different from the random, and therefore, the first impression is that there is association between these two variables. If they look alike or look reasonably similar to the eye, then one could say that there is no association. In this case they look different, and therefore, we can say that there is association. So, how different and all those depends on how we understand the pictures, but I am sure most of us would agree that these two pictures are not similar, they look different, and therefore, there is some association between the salary and the saving. Now, how do we describe association? In terms of many things, the trend. So, is there an upward or a downward association, which means as x increases does y increase, or as x increases does y decrease. We could look at curvature, which means is it linear, it is a straight line, or does it show a curve. And then we look at variation, are points tightly clustered along the line, or they are farther away, and then are there outliers, are there points that should not be belonging completely away, are there surprises, and so on. So, we will try to look at some of these in this lecture. Now, if we look at another set of data on salary versus savings, and let us say this is how the data looks with x as the salary and y as the response variable, which is the saving. Now, if we try to do the randomized picture of this, where we still have 100 points, but the x and y are now sorted completely randomly, which means they do not have the old x y pair, and when we do a similar exercise, this is how the original data looked, this is how the randomized data looks, and do they look different? Maybe they do not. I mean, if we look at it very carefully, one might say they look different, but to the eye one might get a feeling that both of them look a little cluttered, and here we might conclude that there is actually no association between this, or very little association between this. So, if in the previous example we saw that there is a vast difference, so we said there is association, here there is not so much of a difference. So, we said maybe there is not so much association. But then how do we compute? Is there a measure or is there a metric that tells us there is association or there is no association among these variables? We will see those metrics as we move along. Now, to do this, let us take this kind of a data and then we try to plot the x bar and y bar, and that is shown in this picture. This point is our x bar y bar that we can calculate. Now, we have already seen this measure called covariance. So, we visit the covariance again. Covariance quantifies the strength of linear association between two numerical variables. It measures the degree to which data concentrates across the diagonal. So, given x1 y1 and x2 y2 and an x bar y bar, the covariance is given by x minus x bar into y minus y bar by n. I have also raised a question, is it n or is it n minus 1? We can assume n, and later when we find out correlations and other measures, we consistently use the same denominator so that there is no bias in the calculation. So, we use n in this case, x minus x bar into y minus y bar by n is the covariance between these two. So, again the same picture where the averages are shown. So, when we do this, the first picture, when we have this picture, which we go back to this is the original data and this is the random. So, we get back to this picture and then we try to find out x bar and y bar. So, in this picture x bar is 1 2 5 5 2 3 and y bar is 31 9 78. In the random picture, x bar is 1 1 3 4 0 3 and y bar is 1 4 3 8 2. This is not the random picture, this is the second set of data. So, let us go back. This is one set of data, this is data set 1 and let us say this is data set 2, and you can see these two pictures here. So, this is data set 1 which is reflected here, and this is our data set 2 which is here, that is expanded to this. Therefore, they show different x bars and y bars. If there had been the same data and the random, the x bar and y bar would not change because the same 100 values would be used. Therefore, these two represent two different sets of data. This is called data set 1, this is called data set 2. Now, x bar is 1 2 5 5 2 3, x bar is 1 1 3 4 0 3 because the data set is different. Y bar is 31 9 78, y bar is 14 382. So, if we find the covariance of both sigma x minus x bar into y minus y bar by n, summation for all the 100 values, the covariance in the first case becomes 628 232 6586. The covariance in the second case is 527 175 843. So, which has a higher covariance? We quickly calculate the number of digits and then realize that there are 10 digits in this number and there are 9 digits in this number. Therefore, this shows a higher covariance compared to this data. So, what do we make out from these numbers? Generally, what we can make out is if the covariance is higher, there could be some association with the data, and between comparable data sets, the one that has higher covariance seems to have association. So, for the first set of data, x bar is 1 2 5 5 2 3, y bar is 3 1 9 7 8, covariance is 6 2 8 2 3 2 6 5 8 6. And then we calculate standard deviation of x, which is Sx is 148035, Sy is 44851.54. So, standard deviation of x and standard deviation of y are also shown here. Now, we compute the correlation. So, correlation is equal to covariance divided by the product of standard deviations. So, covariance by Sx Sy, so 628 232 6586 divided by 148035 into 44851.54, which is 0.9462. So, correlation for this is 0.9462. We have already studied the correlation coefficient and its computation. So, we are now doing it one more time to show that correlation is 0.9462. Also remember that covariance can be negative, we saw that in an earlier lecture, whereas standard deviations are strictly non-negative, they are either 0 or positive. And because correlation coefficient is covariance divided by a positive quantity, we would have correlation as a negative quantity as well as a positive quantity. The range is between -1 and +1, and in this case we have a correlation of 0.9462, which is very close to 1, and then we could say that the data is indeed associated. Now, if we look at this data, the second set of data, before that let us look at these. Correlation measures the strength of linear association between numerical variables. What is important is linear association between numerical variables. R is always between -1 and +1, and R does not have units. Standard deviation has units. So, Sx has a unit, in this case it is money or rupees. Sy also has unit, which is money or rupees, and then if we go back we do the product of Sx and Sy. So, it is rupee square or money square. Covariance is x minus x bar into y minus y bar by n summation. So, it also has the unit money square, and therefore, correlation does not have a unit. It is a unitless quantity which is between -1 and +1. So, when we look at the second set of data, x bar is 113403, y bar is 14382, s of x is 134858, s of y is 44243.6, covariance is 527175843, and when we compute the correlation we get 0.088. So, correlation is close to 0, and therefore, there is no association or very little association between salary and savings in this case. Now, let us look at another example where we have age of the person versus salary, and let us say we have picked up these 10 points, and then we first plot these 10 points. So, these points, these 10 points are plotted, we get a scatter plot of these 10, and then let us say we also fit a line through a software that we can do, and we want to check this, and we then want to ask a question, is there a positive association or is there a negative association from this data? The line seems to say that there is, looks like, at least for the data that we have looked at, there is a negative association between age and salary, because which is also given by a computed correlation coefficient of -0.227. Now, there is an outlier that we can think of, which is well away and outside. So, it answers all the 4 questions that we looked at. So, there is an outlier in this example. It is also possible to find the correlation when we have more than 2 numerical variables. So, we have age, we have height, and we have weight. Let us say we have this data for boys in the age group of 11 to 20, and let us say we picked up one person with age 11, one person with age 12, and so on, and that is the height and weight respectively. So, correlation between age and itself is 1. So, in this example we can compute the correlation between age and height, which works out to be 0.9015, and you can do the rest of it. Correlation between height and height is also 1, and correlation between weight and weight is also 1. Correlation between age and height is the same as correlation between height and age, and therefore, this matrix will be a symmetric matrix with 1 across the diagonals. So, effectively it is enough to find only 3 numbers: age versus height, height versus weight, and age versus weight. Similar exercise you can do that. Let us say the marks obtained in 3 subjects, mathematics, English and science, by high school students are given. So, we could do that and we could complete this table. Now, let us look at another set of data. So, here we look at the age that is given here and the salaries are also given here. Another set of data. So, we did a correlation and we get correlation is equal to 0.8806. So, if we fit a line, we show the line that is fit, which is shown here, and this line, as I mentioned also in an earlier lecture, has something called R square, which is the goodness of fit, which is 0.7756, and then we also realize that this R square is actually the square of the correlation coefficient of 0.8806. So, 0.8806 square becomes 0.7756. But all this is true only if we decide to fit a straight line. This association holds. If we fit a curve, then we have to have different types of association. We already saw that covariance or correlation is a measure of linear association between numerical variables. So, correlation measures the strength of linear association between variables. Larger R, absolute value of R, becomes more closely the data clusters along the line. We can use R to find the equation of this line and we can predict y for a given x. We can do all this when we have the correlation coefficient. And if we consider the z score, we have not yet come in detail about z score, but z score is the deviation from the mean divided by the standard deviation. Correlation converts the z score of one variable into the z score of another variable. So, there are these mathematics that I have given, the equations that I have given. So, zx is x minus x bar by s, zy is y minus y bar, and then we can have the equation of the line is z bar y is equal to r into zx, and from this we can get a and b that are associated with the line. And we are just showing this computation. So, again this data correlation is 0.8806. So, you can use this calculation from x bar, y bar, sx, xy and r, and from this we can quickly get b, which is 9473.28, and then we can get a, which is minus 222495, and if we actually fit that using the line on using a software, we would get 9473.8. We got 9473.28 in our calculation, a small approximation. Minus 222514 was calculated as 222495. R square was 7756, correlation is 0.8896. We have shown similar pictures, and here I have actually shown how curves are there and how these curves are also fit for this kind of data, but we will restrict ourselves to linear association. But we have to understand that analysis for R is only for linear association among these. Now, we also have to understand one thing through which we look at it through another set of data. Now, let us show two sets of data. Let us assume that this are CAT scores, are exam scores of 6 students, and let us say these are data which correspond to scores made by a cricketer in 6 innings. So, we could treat one of them as a x variable and we could treat the other as a y variable, and then if we only apply the math and try to find the correlation, we get R is equal to 0.7834. So, if I had not told you that this set of variables represent, let us say, CAT scores, and this set of variable represents runs made by a cricketer, and if I simply had withheld this and had simply asked find the correlation coefficient, you will get 0.7834. And if I had asked a question, is there an association, then you might say yes, there is a reasonably high correlation, maybe there is an association between this x and this y. But the moment we say that this represents, say, a CAT score and this represents the runs made by a cricketer, so we realize that there need not be and will not be an association. So, better knowledge of variables can help us understand causation. So, scatter plots and correlations reveal association, they do not tell us causation. For example, they do not tell that if this is the x variable, then I calculate the y variable, I can apply the math and calculate a number, but how well I interpret the number will actually depend on the variables that we are studying, and it is important to know those variables first before we even attempt to find is there a cause and effect between these two variables. But just by themselves, without defining what these variables are, if there is an association, yes, there is an association with a high value of R. So, with this we complete this lecture, and in the next lecture we would look at some numerical examples of association among numerical variables, after which we will start studying probability in further detail.